A black hole holds the universe's most terrifying secret. It is a place where physics breaks, where light cannot escape, and where time itself is stretched and twisted. But what if that cosmic monster is not just a destroyer, but also a key? What if the very thing that swallows stars could also unlock the doors to yesterday and tomorrow? We are about to journey through 30 mind-bending theories that connect the enigma of time travel to the profound mystery of black holes. By the end, you will see the fabric of reality in a completely new way. We will explore tunnels through space, loops in time, and quantum puzzles that make the impossible seem plausible. So, what single idea about time captivates your imagination the most? Our journey begins with a bridge built by pure mathematics, a theoretical shortcut through the cosmos. In 1935, Albert Einstein and his colleague Nathan Rosen tackled the equations of general relativity and found something startling. Their calculations revealed that the extreme curvature of space around a massive object like a black hole might not simply create a bottomless pit. Instead, it could potentially connect to another region of space or even another universe through a tunnel. This hypothetical structure became known as an Einstein-Rosen bridge, though you likely know it by its more popular name, a wormhole. Picture the universe not as a flat sheet, but as a folded piece of paper. Two distant points on that sheet are far apart in the normal, unfolded sense. But if you could create a tunnel that goes directly through the fold, connecting those 2 points, the journey becomes instantaneous. That tunnel is the wormhole with its narrow central passage called the throat. But there is a monumental problem. According to the math, these bridges are incredibly unstable. The moment anything, even a single photon of light, tries to pass through, the throat would snap shut faster than it could be traversed. It would be like trying to run through a hallway that collapses behind you and in front of you simultaneously. To make such a tunnel traversable, science fiction and some theoretical physics suggest a need for something truly bizarre, exotic matter. This is not just antimatter, but a substance with negative energy density, which would exert a kind of anti-gravity, propping the throat open against its own urge to collapse. While we have glimpsed tiny quantum effects that resemble this, we are nowhere near creating or finding enough to hold open a cosmic shortcut. Yet, this theory remains the cornerstone of time travel speculation for a profound reason. If one end of a wormhole could be moved at near light speed while the other remained stationary, Einstein's theory of relativity tells us time would pass differently for each end. You could then step into the stationary end and exit the moving end, not just in a different place, but in a different time. It is a blueprint, a proof of concept written in the language of space-time itself, showing that the universe's geometry does not forbid such journeys. It simply makes them fiendishly difficult to engineer. The wormhole is a theoretical machine, a constructed tunnel through space. But what if time travel is not something we build, but a path that already exists, woven into the fabric of a spinning cosmos? This brings us to our second theory, closed timelike curves. In Einstein's universe, your path through the combined dimensions of space and time is called your world line. Normally, this line always points forward from your birth to this moment and onward. A closed time-like curve is a solution to the equations of relativity where this world line loops back on itself. It is a path through space-time that, if you followed it, would bring you back to an event in your own past. You would not need a tunnel or a machine. You would simply need to follow the curve of the universe itself. The brilliant mathematician Kurt Gödel, a close friend of Einstein, actually discovered such a possibility. He was not looking for time travel, he was exploring the foundations of the universe. In a model of a rotating cosmos, where the entire universe is spinning like a vast, slow whirlpool, Gödel's equations revealed that closed time-like curves could naturally exist. If you traveled on a long enough journey in such a spinning universe, you could eventually return to your own starting point in both space and time. It was a stunning revelation, proving that time travel to the past was not explicitly forbidden by general relativity. The universe's own rotation could, in theory, twist space-time into a loop. This immediately raises one of the most famous puzzles in all of science fiction and philosophy, the grandfather paradox. If you traveled back along a closed timelike curve and prevented your own grandfather from meeting your grandmother, you would ensure you were never born. But if you were never born, you could not have traveled back to change the event in the first place. So, would the universe simply not allow you to step off the path? Would some quantum effect stop your hand, or does this paradox suggest that these elegant curves, while mathematically possible, are physically forbidden by some deeper law we have yet to understand? The existence of closed timelike curves forces us to confront the very nature of cause and effect, and whether the universe cares about keeping its own story logically consistent. Gödel's spinning universe offered a cosmic path to the past, but what if we could build a smaller version of that twisting spacetime right here? The third theory gives us a blueprint, and it comes from physicist Frank Tipler. In 1974, Tipler took the idea of closed timelike curves out of the realm of abstract cosmology and into the domain of hypothetical engineering. He proposed that you would not need the entire universe to spin, just an object of unimaginable density, rotating at a significant fraction of the speed of light. Specifically, he calculated that an infinitely long cylinder made of material as dense as a neutron star and spinning fast enough could drag spacetime around it so violently that it would twist into a loop. If you flew a spaceship in a precise corkscrew-like path around this colossal spinning drill, you could find yourself on a trajectory that circles back to an earlier moment. You would be riding the whirlpool of spacetime created by the cylinder's rotation. The concept is staggering in its requirements. First, the cylinder must be infinitely long to avoid the mathematical complications and instabilities that arise at its ends. Second, it must be constructed from something like neutron star matter, where a single teaspoon would weigh as much as a mountain. We have no material science, no conceivable engineering that could even begin to approach such a task. It exists purely in the domain of pencil and paper physics, a demonstration that the laws of relativity do not say no, but our current understanding of matter and energy shout a very loud maybe never. Yet the Tipler cylinder has had an undeniable influence, particularly in science fiction. It provides a semi-plausible mechanism rooted in real physics for writers to craft stories about constructed time machines. It moves time travel from pure magic into the arena of mega engineering, a project for a civilization so advanced it can sculpt space-time itself. It asks us a profound question: if the universe allows for such a structure in its equations, does that mean it is truly possible somewhere, or is it merely a ghost in the math, a sign that we are missing a deeper principle that forbids such paradoxes from ever being realized? The cylinder stands as a monument to a tantalizing idea that time might be a material we could learn to shape. Tipler's cylinder is a feat of impossible engineering, but the universe itself may have already built similar structures in its fiery infancy. Our fourth theory introduces cosmic strings, relics of the Big Bang that could naturally twist time into knots. In the first moments after creation, as the newborn universe cooled and expanded, physicists believe its fundamental forces underwent dramatic phase transitions. Think of it like water freezing into ice, crystals form, and sometimes where those crystals meet, a flaw or crack appears in the structure. Cosmic strings are the cracks in spacetime itself, hypothesized to be infinitely long, thinner than a proton, yet possessing unimaginable density. A single string just a mile long might have the mass of an entire planet, warping the space around it with its intense gravity. For decades, these strings were purely theoretical, but then physicist J. Richard Gott made a remarkable calculation. He proposed that if two such cosmic strings, or even one string moving in a specific loop, were to pass by each other at a significant fraction of light speed, their combined gravitational fields could curve spacetime in a very special way. The geometry would not just bend, it would twist into a closed time-like curve. It would be like two incredibly massive, ultra-fast threads weaving a knot in the fabric of reality, and that knot could be a loop through time. You would not need to build a machine, you would simply need to find this natural cosmic phenomenon and navigate the path it creates. The visual is haunting, two luminous, thread-like defects in the dark void of space, their immense gravity distorting the light from background galaxies into strange, duplicated arcs. As they whip past one another, the space-time between them contorts, forming a temporary bridge that connects a moment to an earlier version of itself. This theory is compelling because it removes the need for exotic matter or infinite cylinders. It relies on structures that might already be out there, drifting through the cosmos since the beginning of everything. But could we ever find one? Astronomers have searched for the signatures of cosmic strings, looking for telltale double images of distant galaxies or unusual patterns in the cosmic microwave background, the afterglow of the Big Bang. So far, none have been conclusively found. Their existence remains a beautiful, mathematically elegant possibility. Yet, the idea that the universe might have woven time loops into its very fabric from the start is a profound one. It suggests that the potential for time travel is not an aberration, but a feature hidden within the geometry of creation, waiting in the darkness between the stars. But cosmic strings are relics of a violent beginning, while the most likely time machines in our universe may be forming right now from the corpses of massive stars. This is our fifth theory, and it centers on a specific spinning kind of black hole. Not all black holes are the simple, static pits we often imagine. Most are born with a furious spin, a legacy of the rotating star that collapsed to create them. In 1963, physicist Roy Kerr found a solution to Einstein's equations that described this very thing, a rotating black hole. A Kerr black hole is not a simple point of infinite density, a singularity. Instead, its intense rotation flattens that point into a ring singularity. And surrounding this monstrous spinning ring is a region of twisted spacetime so extreme it defies intuition, the ergosphere. Picture a black hole not as a perfect sphere, but as a sphere that is squashed at the poles and bulging at the equator due to its spin. Just outside the event horizon, the point of no return, lies this ergosphere. Here, spacetime itself is not just curved, it is being dragged around by the black hole's rotation, like water caught in a powerful whirlpool. The effect is called frame dragging, and it is so powerful that within the ergosphere nothing can stand still. Not a planet, not a spaceship, not even light itself. Everything is forced to move in the direction of the black hole's spin. It is a cosmic carousel from which there is no getting off. This bizarre property led to a remarkable idea from physicist Roger Penrose. He realized that if you could fly into the ergosphere and release an object in a precise split maneuver, you could actually steal rotational energy from the black hole itself. This Penrose process is like entering a spinning merry-go-round, throwing a ball against the spin to slow it down, and using that transferred energy to propel yourself out even faster than you came in. In theory, a civilization could use this to power its cities for eons, harvesting the spin of a black hole. But the implications for time are even stranger. The extreme frame dragging within the ergosphere warps the paths of objects, their world lines, so severely that some theoretical trajectories could become closed time-like curves. If you could navigate the turbulent currents of this spacetime whirlpool with perfect precision, your path might loop back on itself. To a distant observer watching from safety, you would appear to spiral in, complete a loop, and emerge. But from your perspective, you might return to a point in your own past. The visuals here are breathtaking. a luminous accretion disk of superheated gas spiraling into the abyss, its light warped into a halo around the dark shadow of the event horizon. The ergosphere would be a shimmering, distorted shell where space and time lose their ordinary meaning. This is not a gentle theoretical curve. It is a violent, energetic maelstrom where time travel would be a desperate, high-stakes maneuver at the edge of destruction. It suggests that if time machines exist in our universe, they are not clean, quiet tunnels, but the most ferocious and dangerous engines imaginable, where survival is the first and greatest challenge. The ergosphere of a Kerr black hole is a place of violent possibility where the laws of physics strain at their limits. But what if the universe has a built-in safety mechanism, a rule that prevents paradoxes before they can even begin? This brings us to our sixth theory, the Novikov self-consistency principle, proposed by the Russian astrophysicist Igor Novikov. It offers a radical and elegant solution to the grandfather paradox, not by forbidding time travel, but by redefining what it means to change the past. Novikov's principle is disarmingly simple. It states that if time travel to the past is possible, then any actions a traveler takes there must have already been part of history. You cannot alter an established event because your presence and your actions are what always made that event happen. The timeline is a single, self-consistent story, and you are not an editor, you are a character who was always there. Think of history not as a sequence of events written in ink, but as a completed tapestry. From the front, you see the beautiful, finished picture. Time travel, in this view, would be like going to the back of the tapestry where the threads are messy and tangled. You could move around there, you could pull on threads, but from the front, the picture would remain unchanged. Your actions on the backside were simply part of the weaving process all along. Let us paint a narrative scene to make this concrete. Imagine a time traveler who learns of a great historical disaster, a fire that destroyed a priceless library. Determined to be a hero, they journey back to the night of the fire with a modern extinguisher. They sneak into the building, locate the small electrical fault that will start the blaze, and prepare to stop it. But in their nervousness, they knock over an old oil lamp. The spilled oil ignites, and the very fire they came to prevent roars to life. The traveler, horrified, flees as the library burns. From the perspective of the original history, the cause of the fire was always mysterious, an unexplained ignition. The time traveler did not change the past, they fulfilled it. Their presence was the cause. This is the essence of self-consistency. The universe, according to Novikov, would conspire through seemingly random chance, a slipped hand, a misstep, a sudden failure of equipment to ensure that events play out as they always have. Your free will is not taken away, but your choices are channeled along the one path that does not create a logical contradiction. It is a comforting idea in a way, a guarantee that the fabric of reality will not tear itself apart because of a time traveler's mistake. But it is also profoundly strange. It suggests a kind of predestination where every journey to the past was preordained, and every attempt to alter history is an illusion. The past is not a place you visit, it is a role you have already performed, even if you do not know it yet. This principle transforms time from a river you can divert into a closed loop you can only ever follow. The Novikov principle offers a single, unchangeable tapestry of history, but quantum mechanics paints a very different picture of reality, one where every possibility blooms into existence. Our seventh theory merges these ideas into a breathtaking solution for time travel, the many worlds interpretation. In the 1950s, physicist Hugh Everett proposed a radical answer to one of quantum theory's strangest puzzles. In the classic thought experiment, a particle like an electron exists in a blur of all possible states, a superposition, until it is observed. At that moment, it seems to choose a single definite state. Everett asked a profound question: what if it doesn't choose? What if every possible outcome actually happens? In his view, the universe isn't selecting one path, it is splitting constantly and endlessly into a vast multiverse of parallel realities. Every quantum event, every choice, every random occurrence causes the cosmos to branch into new, equally real worlds. In one branch, the electron spins up. In another, it spins down. Both are real. Now, apply this to time travel. You build a machine and journey back to prevent a tragedy. Under the many worlds view, you do not arrive in your own past. The moment you appear in that earlier era, you cause a quantum split. You have entered a new, parallel universe that is almost identical to your original history up to that point. In this new branch, you intervene. You save the day, you alter events. The future of that new universe unfolds differently with you in it, but your original timeline, the one you came from, remains untouched and unchanged. The library still burned there. Your younger self still grew up in a world shaped by that loss. You didn't erase your history, you simply left it behind and created a new one. This elegantly dissolves every paradox. The grandfather paradox simply cannot happen because the universe where you prevent your grandfather's meeting is not the universe you were born in. It's a separate branch on the infinite tree of reality. You are not a contradiction, you are an immigrant from a parallel world. This theory has become a cornerstone of modern science fiction for its narrative freedom. It allows for dramatic changes to history without the logical knots. Stories can explore worlds where the knots is one World War II, or where dinosaurs never went extinct, not as altered timelines, but as legitimate branches of the multiverse that always existed. Visually, imagine a single timeline like a glowing strand. The moment the time traveler arrives in the past, that strand splits into two. One branch continues forward as the original history, dim and unreachable to the traveler. The other, brighter branch veers off, carrying the traveler and the consequences of their actions into a new future. It is an infinite tree of possibilities where every mistake can be unmade in another world and every choice spawns a new universe. It is a profoundly liberating yet also isolating idea. You can change things, but you can never go home again because home is on a branch you have now drifted away from. The universe is not a single story, but an endless library of every story that could ever be told. The multiverse offers endless branches, but what if time travel happens on a scale so small we cannot even perceive it? At the quantum level, the rules of our everyday reality dissolve into a haze of probability. Particles can perform seemingly impossible feats like quantum tunneling, where an electron passes straight through a solid wall as if it were not there. It does not go over or around the barrier, it simply appears on the other side, thanks to the fundamental uncertainty baked into the universe. This leads to a wild, speculative theory. Could particles tunnel not just through space, but through time itself? If time is a dimension woven into the fabric of space-time, then perhaps it too is subject to quantum uncertainty. A particle might not have a perfectly defined position in time, just as it lacks a definite position in space. In its probabilistic haze, it could have a tiny, non-zero chance of appearing not just on the other side of a wall, but on the other side of a temporal barrier, briefly existing in a slightly earlier or later moment. The frameworks for this are highly abstract, treating time as a dimension where quantum fluctuations can occur. Some experiments already hint at this bizarre temporal ambiguity. Scientists have performed tests with pairs of entangled photons, where the order of events, what causes what, becomes impossible to define. In certain quantum setups, you cannot say for sure whether event A happened before event B or B before A. The temporal sequence itself exists in a superposition, much like the particle's location. It is as if time, at its most fundamental level, is not a rigid sequence of ticks, but a fuzzy network of possibilities. To visualize this, imagine not a spaceship or a tunnel, but a subatomic particle, a shimmering point of light. It approaches a barrier that represents a moment in time. Instead of moving forward in a smooth line, it flickers, its position blurring. For an instant, its glow appears faintly on the far side of the temporal barrier, a ghost from a future or past probability, before snapping back to its expected path. This is not time travel as a journey, but as a fleeting statistical glitch in the machinery of reality. It suggests that if time travel is possible, its roots may not be in massive cosmic engineering, but in the inherent probabilistic fuzziness of the quantum world. The universe may already be doing it particle by particle, moment by moment, in a silent dance we are only beginning to detect. Quantum particles may flicker through time, but a human-scale journey requires a vessel. In 1994, physicist Miguel Alcubierre offered a blueprint for one, a concept that bends the fabric of space itself to achieve the impossible. The Alcubierre warp drive does not propel a ship through space at faster than light speeds, which Einstein's laws forbid. Instead, it manipulates space-time around the vessel. Imagine a sleek spacecraft sitting inside a bubble of normal space. Behind the ship, the drive would expand space-time, pushing that region outward. In front, it would compress space-time, pulling the destination closer. The ship itself remains motionless inside its bubble, a passenger on a moving sidewalk made of the cosmos. Within that pocket of calm, the laws of physics hold firm, but outside, the stars would streak past as the bubble itself travels, in theory, faster than light. The visual is iconic, a silver craft cradled within a shimmering distortion, with stars ahead bunched into a brilliant blue haze and stars behind stretched into reddened streaks. But this is not just about crossing vast distances, it is a direct ticket to the future. The intense warping of space-time creates a severe form of time dilation. For everyone inside the bubble, time would pass normally. A journey of a few months might feel exactly that, but outside the bubble, in the rest of the universe, centuries or millennia could rush by. Upon arriving at a distant star and turning off the drive, the travelers would step out into a universe that had aged enormously without them. They would have effectively time traveled into the future, not by moving through time, but by letting the universe's time race past them while they were shielded inside their warp bubble. The catch, and it is a monumental one, is the engine's fuel. To create the necessary compression and expansion of space-time, the Alcubierre drive requires something we have only theorized: exotic matter with negative energy density. This is not merely a powerful energy source, it is a substance that would generate a kind of anti-gravity, warping space-time in the opposite way normal matter does. While quantum physics suggests tiny amounts of negative energy might be possible, the scale needed for a warp drive is astronomically beyond our reach. Furthermore, some calculations suggest that once such a bubble is created, the region inside it could become causally disconnected from the outside universe, potentially creating a closed timelike curve. This raises a startling possibility that a ship using a warp drive might not just jump forward in time from an external view, but that the crew, by steering their bubble on a specific loop, could potentially return to their own past. The warp drive thus sits at a fascinating crossroads, a concept born from hard math that promises the stars, but in doing so, might also hand us the keys to time itself, if only we could find the impossible material to build it. The warp drive bends space to cheat time, but one form of time travel is not theoretical at all. It is a confirmed prediction of Einstein's universe. Theory 10, black hole gravitational time dilation, is one of the most rigorously tested pillars of general relativity. The core principle is this: gravity does not just pull on objects, it pulls on time itself. The stronger the gravitational field, the slower time flows relative to a weaker field. A clock at sea level ticks ever so slightly slower than a clock on a mountaintop because Earth's gravity is marginally stronger at the lower altitude. Now amplify that effect to the extreme environment of a black hole. An astronaut in a stable orbit just outside the event horizon would be immersed in a gravitational field of unimaginable power. For them, time would pass at what felt like a normal rate. Their heart would beat, their thoughts would flow, one second following another. but to a distant observer watching from the safety of Earth, that astronaut's clock would appear to be ticking with agonizing slowness. Every minute for the astronaut could be years, decades, or even centuries for those back home. This is not science fiction, it is the direct consequence of mass warping spacetime. The astronaut, by simply surviving near the black hole, becomes a time traveler to the future. They are not moving through time, they are letting the universe's time rush past them while they linger in a gravitational slow-motion zone. When they finally break orbit and return to Earth, they would find the planet aged enormously, a living relic from their own distant future. The film Interstellar provided a stunning and scientifically grounded portrayal of this very effect. The crew visits a planet named Miller's, which orbits dangerously close to a supermassive black hole called Gargantua. For every hour they spend on that planet's surface, 7 years pass on Earth. In a heart-wrenching sequence, the crew returns to their orbiting mothership after a few hours to find their colleague has aged over 2 decades, waiting for them. The math behind this is both beautiful and staggering. The time dilation factor depends on the black hole's mass and the astronaut's proximity. For a stellar mass black hole, just 10 times the mass of our Sun, orbiting at a point where the gravitational pull is survivable, you might experience a dilation where one of your days equals about a month on Earth. But for a supermassive black hole like the one at the center of our galaxy, which has millions of times the Sun's mass, the effect near its event horizon is far more extreme. There, 1 hour for the astronaut could equate to several years elsewhere. Imagine the visuals, side-by-side clocks on a screen. One clock, labeled Earth, spins its hands in a frantic blur, its digital counter racing through years. The other, labeled astronaut, ticks forward with a slow, deliberate precision. We see the astronaut in their cockpit, watching a monitor that shows a sped-up history of Earth, civilizations rising and falling, cities blooming and vanishing, in what feels like a single afternoon of their life. They are a spectator to the future, isolated in a bubble of slowed time at the edge of oblivion. This is the ultimate one-way ticket, a journey with no return to the world you knew. You step out of your ship not as a hero returned, but as an artifact from a forgotten past, a ghost in a new age. A black hole's event horizon is a one-way door where nothing, not even light, can ever return. But what if every entrance has an exit? The equations of general relativity are, in a deep mathematical sense, time-symmetric. They work just as well if you run the clock backward. This leads to a stunning theoretical counterpart, the white hole. If a black hole is a cosmic drain from which nothing escapes, a white hole is a cosmic fountain from which nothing can enter. It is a region of space-time where matter and energy can only erupt outward, violently and continuously, as if the universe itself were being born from a single, radiant point. The mathematics does not forbid it. A white hole is simply a black hole with time reversed. Picture not a dark abyss, but a brilliant, searing geyser of light and plasma, spewing galaxies worth of material into the void. It would be the most luminous, energetic object imaginable, a primal shout against the silent dark. The most tantalizing idea is that a black hole and a white hole might not be separate objects, but two ends of the same cosmic tunnel, connected through the throat of an Einstein-Rosen bridge. In this view, everything that falls into a black hole in our universe might not be crushed into oblivion at a singularity. Instead, it could be hurled out through a white hole, perhaps into another universe entirely, or even into a different time in our own. You could think of it as a cosmic recycling plant, where our universe's used space-time is reborn as the raw material for another. This offers a potential mechanism for time travel or interdimensional travel that is written directly into the fabric of relativity. Yet, for all its mathematical elegance, most physicists consider white holes physically improbable. The reason lies in the second law of thermodynamics, the law of entropy, which states that disorder in a closed system always increases. A white hole erupting perfect, ordered energy into the cosmos would appear to decrease entropy, like a shattered glass spontaneously reassembling itself. From our perspective in the forward flow of time, such an event is astronomically unlikely. It would require conditions so precise they border on the impossible. Furthermore, any connection to a white hole would be incredibly unstable, likely collapsing the instant it formed. So while the white hole remains a beautiful ghost in the equations, a testament to the symmetry of Einstein's universe, it is a door we have never seen open, a fountain that may forever remain dry. It whispers of a cosmos where every ending is a beginning somewhere else, even if we are forever trapped on this side of the horizon. White holes may be improbable cosmic fountains, but their theoretical existence highlights a deeper question. Does the universe actively guard its own history? Stephen Hawking, the legendary physicist who devoted his life to unraveling black holes, once pondered this very problem. He looked at the equations that seemed to permit time travel and felt a profound unease. The potential for paradoxes where an effect could loop back to become its own cause struck him as not just strange but fundamentally wrong. In response, he proposed something bold, the chronology protection conjecture. Hawking suggested that the laws of physics, particularly the wild and unpredictable laws of quantum mechanics, contain a built-in safety feature. This feature would prevent closed timelike curves from forming on any scale large enough for a human or even a molecule to traverse. It is not a proven law, but a powerful hypothesis, a bet on the universe's own sense of order. The proposed mechanism is as beautiful as it is destructive. In the quantum vacuum of empty space, particles and their antiparticles are constantly flickering in and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other. These are virtual particles, the seething foam of spacetime itself. Normally, their effects average out to nothing, but Hawking and others calculated that near a potential time machine, like the throat of a wormhole or the region around a rapidly spinning cylinder, these quantum fluctuations would not cancel out. Instead, they would feed back on themselves, growing more and more violent. The energy density of the vacuum would skyrocket, becoming infinite, creating a firewall of raw quantum fury that would obliterate the time machine before it could ever be used. Imagine a delicate machine, its rings spinning, its exotic matter holding open a shimmering gateway. As it powers up, the very emptiness around it begins to shimmer with unnatural light. Virtual particles, usually invisible, flash into reality not as fleeting pairs but in a cascading storm. The space around the machine's throat crackles with impossible energy, a blinding, chaotic tempest of creation and destruction. The machine strains, its structure vibrating, and then, in a flash of transcendent light, it is torn apart from the inside out by the universe's own immune response. The conjecture is a cosmic veto, a statement that the universe abhors a paradox as much as nature abhors a vacuum. But is it a fundamental law or just a sign of our current ignorance? The debate is fierce. Some physicists argue that Hawking's intuition was correct, that chronology protection is as essential a feature of reality as the speed of light. They see the infinite energy buildup not as a flaw in the calculation, but as proof that such configurations are physically impossible. Others are more skeptical. They point out that our understanding of quantum gravity, the theory that would marry general relativity with quantum mechanics, is still incomplete. Perhaps in a full theory, like string theory or loop quantum gravity, these infinities would be tamed and the protection would fail. Maybe there is a way to engineer around the quantum storm, to stabilize the tunnel with some form of physics we have not yet discovered. Hawking himself, ever the provocateur, once said he wanted time travel to be impossible because otherwise, where are all the tourists from the future? His conjecture stands as a guardian at the gates of history, a mathematical sentinel. It suggests that if we ever hear the call of yesterday, the universe itself might rise up in a storm of light to silence it. Hawking's conjecture builds a wall of quantum fire to protect history, but some theories propose a messenger that could simply fly over it. Enter tachyons, hypothetical particles born from a twist in Einstein's own equations. The theory of relativity sets the speed of light as the universe's ultimate speed limit for any object with mass. But the math itself does not forbid the existence of particles that are born already moving faster than light. These are tachyons from the Greek word for swift. Their defining, bizarre property is that they would always travel faster than light, and they could never slow down to or below that cosmic speed limit. To do so would require infinite energy, just as pushing a normal particle to light speed would. But the true strangeness lies in their relationship with time. According to the equations of special relativity, as an object approaches the speed of light, time for that object slows down relative to the rest of the universe. If you could reach light speed, time would stop. Tachyons living permanently on the other side of that barrier flip the script. For a tachyon, time itself would appear to run backward. From our perspective, a tachyon's journey from point A to point B would be a streak of impossible speed. But from the tachyon's own hypothetical point of view, it would be traveling backward in time. Its cause would come after its effect. This opens a dizzying possibility. If we could somehow create, detect, or control tachyons, we might be able to encode a message on one. That message could then be sent not just across space but backward along the timeline. Imagine a scientist in a laboratory. They fire a tachyon beam at a detector. The instant it hits, the detector prints out a message, but the message reads, "Do not fire the beam." The tachyon, carrying information from the future moment of its detection, has traveled back to the moment before it was even sent, creating a loop of information with no clear origin. The visual is mind-bending. Picture a standard timeline, a glowing line from past to future. Normal particles are little sparks moving steadily forward along it. A tachyon appears as a brilliant, streaking particle that zips forward, but leaves a ghostly, inverted trail behind it, showing its path backward through time. It is a paradox made manifest, and this is precisely why most physicists are deeply skeptical. Tachyons raise catastrophic causality problems. If you can send a message to your own past, you could instruct your past self to never send the message, creating an instant logical contradiction. The universe, it seems, would rather banish entire categories of particles than allow such nonsense. This is likely why we have never found a shred of evidence for tachyons despite searches. They may be mathematical phantoms, solutions to equations that reality itself rejects. Yet they persist in our imagination because they represent a pure, almost elegant form of time travel, one built not into the curvature of space, but into the very nature of a particle. They ask us if the universe's speed limit is not just a barrier, but a one-way mirror with an entirely different kind of physics operating on the other side, where time flows in reverse and every signal is an echo of its own future. Tachyons vanish into the paradox of their own making, but another riddle remains, one where the object itself is the mystery. This is the bootstrap paradox, a loop of existence with no beginning. Sometimes called the ontological paradox, it occurs when an object, a piece of information, or even a person is sent back in time, and that very item becomes the essential cause of its own existence in the future. It creates a closed loop of origin, a circle with no starting point. The object seems to have just bootstrapped itself into reality, hence the name. Think of a composer struggling with a blank page who receives a package from a mysterious stranger. Inside are the complete, masterful scores for 9 symphonies. The composer, in awe, publishes them under their own name, becoming celebrated as a genius for centuries. Decades later, now old and famous, they finally build a time machine. Their one mission, to ensure their own legacy. They travel back in time, locate their younger, struggling self, and deliver a package containing the very same 9 symphonies. Where did the music originally come from? Who composed it? No one ever did. It simply always existed, trapped in an infinite loop of being given and received. The notes were never born from inspiration, they were forever caught in a cycle of delivery. The visual sequence is haunting. We see a beautiful, leather-bound book materialize in a flash of light on a desk in the past. A young writer discovers it, copies it word for word, and becomes a literary legend. In his old age, worn and frail, he holds the same book. With trembling hands, he places it into a time machine, setting the coordinates for his own past. The book vanishes, and we watch it reappear in that flash of light on the desk, completing the perfect, unbreakable circle. The pages are never blank, the ink never fresh. It is a relic with no creator. This paradox strikes at the heart of creation and destiny. It asks whether something can be real, can have tangible effects on the world, without ever having been invented or authored in the conventional sense. It suggests a universe where certain ideas or artifacts are not created, but are simply eternal features of the timeline, waiting to be discovered by traveling along their own loop. Philosophically, it challenges our deepest notions of cause and effect. Everything we know has an origin story, a chain of events that led to its existence. The bootstrap paradox severs that chain, offering a dizzying alternative where the thing is its own cause. It is a cosmic Ouroboros, the snake eating its own tail, made manifest in reality. If such loops are possible, then the history of art, science, and knowledge could be littered with bootstrapped objects, their true origins forever lost to time's closed curves. We might be admiring melodies that never had a composer, reading truths that never had a discoverer, in a universe where some things simply are because they always were. The bootstrap paradox presents a loop with no origin, but another physicist found a way to resolve a potential collision with pure geometry. Joseph Polchinski proposed a brilliant thought experiment that strips time travel down to its most basic elements: a billiard ball, a wormhole, and a single decisive impact. Imagine a billiard table with a wormhole at one end. This wormhole is special. Its exit is not in another place, but a few moments back in time. Now picture a single billiard ball rolling across the felt. It heads straight for the wormhole's entrance and disappears inside. An instant later, it emerges from the wormhole's exit, which is positioned just to the side of the table, but a few seconds in the past. This older, time-traveling ball now rolls onto the table just as its younger self is approaching the entrance. The two balls collide. The impact is perfect, a glancing blow that sends the younger ball veering off course, just enough so that it misses the wormhole entrance entirely. It rolls harmlessly across the table and off the far side. But here is the stunning question: if the younger ball never went into the wormhole, then where did the older ball that emerged to hit it come from? This seems like an instant paradox, a universe-breaking contradiction. Yet Polchinski, applying the Novikov self-consistency principle, showed there is one and only one possible outcome that avoids a paradox. The collision must happen in exactly the right way. The time-traveling ball must emerge and strike its younger self with precisely the correct angle and force to deflect it away from the wormhole, while also ensuring that its own post-collision trajectory sends it rolling directly into the wormhole entrance from the other side. In this perfectly choreographed dance, the ball that gets hit is not the one that later travels, and the ball that travels is the one that did the hitting. It is a single, self-consistent loop. The ball's entire history is a closed circle. It emerges, it strikes, it gets deflected into the wormhole, travels back, and emerges again to complete the strike. There is no first time, no starting point in the loop. The visual sequence makes this clear. We see a single ball rolling toward the wormhole. Just before it reaches the entrance, another identical ball shoots out from the side, striking it. The struck ball veers away, but the striking ball, now careening from the impact, rolls directly into the wormhole. We then see that same ball emerge from the past exit, becoming the very ball that initiated the collision. The loop is seamless, a single unbroken chain of cause and effect that folds back on itself. This paradox resolved demonstrates that the universe might permit time travel not by preventing change, but by weaving every action into a tapestry where all events are mutually consistent. The billiard ball never had a choice. Its path was the only one that would not tear the fabric of reality. It suggests a cosmos where time travelers are not free agents, but actors following a script they themselves wrote in a future that is also their past. Polchinski's billiard ball found its single, consistent path. But what if the universe offered a vantage point where you could watch eternity unfold in an afternoon? Theory 16 introduces Malamute-Hogarth spacetimes, a class of bizarre cosmic geometries where the very meaning of infinite time is rewritten. Named for the philosophers who explored their implications, these are not machines you build, but regions of the universe where spacetime is curved in a profoundly specific and extreme way. In such a spacetime, two observers can have radically different experiences of time. One observer, let us call them the traveler, takes a specific finite-length journey. For them, their wristwatch ticks forward a set amount, perhaps a few days or years. But a second observer, stationed at a special point in this warped geometry, would witness something impossible. From their fixed vantage, they would see the traveler's entire journey take an infinite amount of time to complete. The traveler's finite proper time is stretched from the stationary observer's perspective across eternity. This is not an illusion or a trick of perception. It is a direct consequence of the spacetime's severe curvature, which distorts the light cones, the pathways that information and causality can travel. In a Malamute-Hogarth spacetime, the traveler's world line remains within a finite span, but the stationary observer's past light cone, the region of spacetime from which they can receive signals, encompasses the traveler's entire infinite-length history. The visual is a masterpiece of cosmic distortion. Picture a standard diagram of spacetime as a grid. Now, twist and warp that grid into a peculiar funnel shape. One path, the traveler's, spirals tightly through the neck of the funnel, completing a loop in a short distance. Another point, the stationary observer's, sits at the wide mouth of the funnel. Light cones, usually depicted as neat 45-degree diamonds, are now stretched into long, thin tiers, their tips pointing in strange directions. From the observer's point at the mouth, looking down the funnel, they see the traveler's entire spiral path laid out like an infinite thread. The implications for computation and knowledge are staggering. Imagine you are the stationary observer, and the traveler is a powerful computer programmed to solve a problem. There are certain mathematical questions, like whether a computer program will eventually halt or run forever, that are fundamentally unsolvable by any finite computational process within our normal time. But in a Malamute-Hogarth spacetime, you could send the computer on its journey. For the computer, it runs its calculation for what feels like a finite duration. But from your perspective, you wait an infinite amount of time for the answer. If the program never halts, you would simply watch it run forever. But if it does halt at the precise moment it finishes its finite computation, a signal from that event would finally reach you carrying the answer. You would have received the solution to an otherwise unsolvable problem. This connects directly to black holes. Some theoretical models suggest that the regions near certain types of singularities, or the extreme environments around charged and rotating black holes, could approximate Malamute-Hogarth conditions. An intrepid researcher could dispatch a probe into such a region. The probe performs its measurements or computations over its own finite lifespan, and then, as it reaches a critical point, beams of final data burst back to the researcher safely orbiting farther out. Due to the extreme gravitational time dilation, that single burst of data could represent the culmination of an infinite amount of processing from the researcher's frame of reference. It would be like receiving a message that condensed the work of forever into a single packet. This is not time travel in the classic sense, but it is a form of cheating time itself, leveraging the universe's own curvature to accomplish the infinite. It proposes that some answers are not beyond us. They are simply waiting in the right kind of twisted corner of reality, where a finite journey can cast an infinite shadow. Malamud-Hogarth spacetimes twist time into a tool for infinite computation, but at the quantum level, time might not even have a definite order. The 17th theory pushes into truly alien territory where the present can reach back and touch the past. Quantum entanglement, that spooky action at a distance, links particles so intimately that measuring one instantly determines the state of its partner, no matter the distance separating them. This connection defies our everyday notions of locality, the idea that objects are only influenced by their immediate surroundings. But what if this non-locality is not just a feature of space, but of time itself? Some interpretations of quantum mechanics suggest that entangled particles are not truly two separate entities, but two aspects of a single, unified quantum state that exists across spacetime. Their connection might transcend not just miles, but moments. This idea is probed by mind-bending experiments like the delayed choice quantum eraser. In these setups, a photon is given a choice to behave like a particle or a wave, and that choice is recorded by a detector. But here is the twist: information about which path it took can be erased by a second, entangled photon after the first has already been measured. Astonishingly, the results seem to indicate that the erasure of information in the present can retroactively change whether the first photon behaved as a particle or a wave in the past. It is as if the photon's history is not fixed until the final piece of information is gathered, challenging the very idea of a linear, immutable timeline. The visual for this is abstract and beautiful. Picture not a timeline, but a shimmering, nebulous cloud of probability. Within it, two particles are represented not as dots, but as intertwined, glowing filaments. A measurement event is a flash of light at one filament. Instantly, a corresponding flash appears on its partner filament, but the glow also seems to travel backward along the first filament, as if rewriting its recent history into a new, consistent pattern. Diagrams show the classic entangled pair, but with their world lines not just parallel but looped and braided, suggesting their causal connection cannot be drawn as a simple arrow from past to future. This leads to a staggering speculation. If we could create and manipulate entangled particles with exquisite control, could we use them to send a signal, not just across space but backward through time? Imagine preparing a pair of entangled particles. You keep one in a shielded lab and send its partner on a journey into the future via severe time dilation near a black hole. The future observer then measures their particle, collapsing its state. According to some interpretations, that measurement could instantaneously determine the state of the particle you hold in the past. From your perspective in the past, you would see your particle randomly assume a definite state. But with pre-arranged codes, that random change could be decoded as a message from the future. It would be a quantum whisper from tomorrow, etched into the present. The universe, however, seems to have safeguards. No experiment has ever allowed useful information, like a specific word or number, to be sent this way. The randomness of quantum measurement prevents a clear causal signal. Yet, the mere possibility that the present and future might be linked in a coherent, non-local quantum state reshapes our understanding of time. It suggests that at its most fundamental level, time may not be a sequence of moments, but a vast, interconnected network where cause and effect can sometimes dance in both directions. The past may not be a distant country, but a partner particle forever entangled with the now. Quantum entanglement suggests a universe woven together, but what if our entire three-dimensional reality is just a projection? The holographic principle proposes exactly that, a radical idea born from the fiery paradox of black holes. It begins with a simple, profound question: what happens to information when it falls into a black hole? According to quantum mechanics, information can never be truly destroyed. It might be scrambled, but it must be preserved in some form. Yet, a black hole's event horizon seems to be the ultimate shredder. Anything that crosses it is lost forever from our universe, and if the black hole eventually evaporates via Hawking radiation, that information would seemingly vanish, violating a core quantum law. This is the black hole information paradox, a clash between general relativity and quantum theory that has kept physicists awake for decades. The holographic principle offers a stunning escape. It suggests that all the information describing everything within a three-dimensional volume of space, every star, every planet, every person, is not stored within that volume at all. Instead, it is perfectly encoded on the two-dimensional boundary that surrounds it, like a cosmic film projected onto the surface of a sphere. Think of a hologram on your credit card. The flat, shiny sticker contains all the data needed to project a three-dimensional image that seems to float in space. The universe itself might work the same way. Our rich, three-dimensional experience of depth, of moving through space, could be a magnificent illusion generated from information painted on a distant, two-dimensional surface. For a black hole, this boundary is its event horizon. The principle suggests that when matter falls in, its information is not crushed inside. It is smeared and encoded onto the horizon's surface, pixel by pixel, in unimaginably tiny units of area called Planck lengths. The black hole's interior, the terrifying three-dimensional void, is a projection from the data on its two-dimensional skin. This means the information is never lost, it is just translated into a form we do not yet understand. The evaporation of a black hole through Hawking radiation is not a deletion, but a slow, careful reading of that encoded data, played back into the universe as it shrinks. Now stretch this idea to its ultimate limit. If the entire cosmos is holographic, then the past is not gone. It is recorded. Every event, every photon's path, every conversation could in theory be encoded on the boundary of the observable universe. The surface of that colossal sphere holds a perfect, if indecipherably complex, record of everything that has ever happened within it. It is the universe's ultimate hard drive. Imagine a visual, a glowing, three-dimensional scene of a galaxy swirling in the void. Then the camera pulls back, and we see that this entire scene is being projected from a vast, shimmering, two-dimensional membrane that encircles it. The stars, the dust, the light, all are just vibrations on that flat surface. For a black hole, we would see an object falling toward the dark sphere. As it touches the event horizon, it does not vanish into darkness. Instead, it flattens, its information imprinting itself as a brilliant, intricate pattern on the horizon's surface, like a splash of paint on a canvas, forever preserving a record of what fell in. This leads to a breathtaking speculation for time. If we could ever learn to read that cosmic code on the boundary, we would not be traveling to the past. We would be replaying it. We could reconstruct any event in history with perfect fidelity, not by moving through time, but by accessing the universe's own immutable recording. It turns the cosmos into a vast, timeless library, where every moment that ever was is forever etched onto the walls of space itself, waiting for a reader with the right eyes to see. The holographic universe is a timeless library, but its most dangerous archives may be hidden behind a spinning ring of fire. Deep within a rotating Kerr black hole, past the point of no return and beyond the violent ergosphere, lies a structure that defies all intuition. A crushing singularity is not a point but a ring, a luminous loop of infinite density spinning at a significant fraction of light speed. This is the ring singularity, and it is the heart of a potential cosmic gateway. The mathematics of general relativity suggests a staggering possibility that an object surviving the journey through the event horizon might not be crushed at the center. Instead, if it could navigate the chaotic tides, it might pass through the whole of this donut-shaped singularity, and on the other side, the equations do not end in oblivion. They open up, describing pathways to other universes or to different regions and times within our own. It is as if the black hole is not an end but a tunnel, with the ring singularity acting as its luminous, impossible portal. Picture a spacecraft having somehow survived the crossing of the event horizon. It is now irrevocably falling inward. All paths lead toward the center, but the crew fights to steer, using every ounce of thrust to maneuver in this gravity-warped space. Ahead, in the profound darkness, a shape begins to glow. It is not a solid sphere, but a brilliant, thin circle of tortured light spinning furiously. It looks like a cosmic ring of fire, a burning hoop from a nightmare. The space around it shimmers with gravitational lensing, and the very fabric of reality seems to tear at its edges. This is the ring singularity. The theory posits that if the ship could align its trajectory perfectly, it could plunge through the hole in the center of that ring. For a fleeting instant, it would be surrounded by infinite curvature, a place where the laws of physics as we know them cease to have meaning. And then it might emerge not into crushing density, but into another space-time entirely, perhaps a white hole erupting in a different cosmos, or a distant region of our own universe in another time. But this potential gateway is guarded by a ferocious and unstable sentinel, the inner Cauchy horizon. This is a theoretical boundary that lies between the event horizon and the ring singularity. It is a region where, from a mathematical perspective, predictability itself breaks down. The Cauchy horizon is where the influence of the world outside the black hole theoretically ends, and where wild, uncontrollable fluctuations run rampant. Any matter or radiation that has ever fallen into the black hole, from its formation billions of years ago to the present moment, would appear to be focused and concentrated at this inner boundary. The result would be an infinite buildup of energy, a wall of blue shifted radiation of every wavelength that has ever entered. In practice, this likely means the inner region is violently unstable, subject to what physicists call mass inflation, where even the tiniest perturbation grows without bound. A real spacecraft approaching the ring would probably be vaporized by this firewall of accumulated cosmic history long before it ever saw the luminous ring. The gateway might exist in the pristine equations, but the universe seems to fill its anteroom with a storm of infinite energy, a final, impassable filter. The visual journey is one of escalating awe and terror. From within the cockpit, the crew sees the universe they left behind compressed into a brilliant, shrinking disk of light above them. Below is only blackness until the ring begins to manifest, a faint, ethereal glow that solidifies into a searing, circular filament. The ship is buffeted by chaotic tides, space-time stretching and compressing in conflicting directions. As they near the inner Cauchy horizon, the instruments go wild, detecting an impossible surge of radiation across all spectra, a blinding, omnidirectional light that seems to carry echoes of every star the black hole has ever consumed. It is the ghost of the black hole's past rising up to guard its secret heart. To pass through would be to gamble with the fundamental stability of reality, to trust that the equations describing a calm ring singularity are not a mirage hiding a lethal quantum mechanical inferno. This theory presents the ultimate cosmic dilemma, a doorway to everywhere and everyone, locked behind a wall of fire at the end of time. It suggests that if time machines exist in nature, they are not just dangerous, they are almost certainly suicidal, placing the greatest possibilities of the universe squarely in its most unforgiving and unstable depths. The ring singularity is a gateway cloaked in fire, but other paths through time require no black holes at all. Hidden within Einstein's own equations are quieter, stranger universes where time loops are woven into the fabric of everything. Long before we understood spinning black holes, other mathematicians were finding these peculiar solutions. One came from a Dutch physicist named Willem Jacob van Stockham. In 1937, he considered a hypothetical scenario, an infinitely long, incredibly dense cylinder made of a swirling cloud of dust, all rotating together like a rigid body. This Van Stockum dust cylinder creates a powerful frame dragging effect, twisting the spacetime around it. His calculations showed that if this cylinder rotates fast enough, the distortion becomes so severe that closed time-like curves form in the space surrounding it. You could orbit this colossal, spinning pillar, and if you followed a precise helical path, return to your own past. It is a simpler, more idealized cousin to the Tipler cylinder, proving that even without exotic matter or event horizons, pure rotation in a specific configuration can bend time into a loop. The visual is stark, a luminous, infinite column against the black of space with shimmering helical paths spiraling around it, each one a potential loop through time. Yet its requirements are just as impossible as they sound, an infinite length and a perfect, rigid rotation of an impossible material. It is a mathematical ghost, a proof of concept, not a practical machine. An even more profound solution came from Kurt Gödel, the genius logician and friend of Einstein. In 1949, Gödel presented Einstein with a birthday gift that shook the great physicist's worldview, a complete model of a rotating universe. Gödel was not trying to build a time machine, he was exploring the logical foundations of cosmology. In his universe, every bit of matter is slowly rotating in the same direction. This cosmic spin, this gentle whirlpool on the scale of everything, has a breathtaking consequence. Gödel's equations explicitly contain closed time-like curves. In this rotating cosmos, if you traveled on a sufficiently long, straight rocket journey, you could eventually return to your starting point in space and time. You would not need a cylinder or a black hole, the entire universe would provide the path. For Einstein, this was deeply troubling. His theory did not forbid time travel, it invited it. Gödel had used the master's own equations to show that the universe could, in principle, be a time machine. The visual for Gödel's universe is mesmerizing. Think of a vast, transparent sphere filled with galaxies. But instead of drifting randomly, they all slowly drift in a gentle, coordinated swirl, like leaves caught in a cosmic eddy. Superimposed on this are faint, glowing loops, world lines that curve back on themselves, showing how a journey in one direction could circle back to its own beginning. These models, the Van Stockum cylinder and Gödel's universe, are not descriptions of our reality. Our universe is not rotating in that coordinated way, and we have no evidence of infinite rotating cylinders. But they are not science fiction, they are rigorous mathematical solutions to the equations of general relativity. Their profound importance lies in what they prove, that time travel to the past is not a bug in Einstein's theory, it is a feature. The universe, according to its own deepest laws of gravity and geometry, can accommodate loops in time. The fact that our particular cosmos does not seem to have them might be our great fortune, or it might be a clue that something else, some deeper principle, actively prevents their formation, protecting the orderly flow of cause and effect we depend on. Gödel's universe showed time loops woven into cosmic rotation, but to see the true fabric of reality, we must look much, much closer. The theories of Einstein and the mysteries of quantum mechanics remain stubbornly separate, and their clash is most violent at the heart of a black hole. To truly understand what happens there and whether time travel is possible, we need a theory that unifies them. This is the quest for quantum gravity, and our 21st theory suggests it may reveal a universe far stranger than we have yet dared to dream. General relativity paints spacetime as a smooth, continuous fabric, bending under the weight of mass. Quantum mechanics shows us a subatomic world of discrete particles and inherent uncertainty. A singularity where gravity becomes infinite and spacetime curves to a point is where these two magnificent theories break down, screaming in contradiction. A complete theory of quantum gravity, like string theory or loop quantum gravity, aims to resolve this. It would describe gravity not as curvature, but as the behavior of unimaginably tiny vibrating strings, or as a woven network of discrete loops. At this scale, the smooth fabric of spacetime dissolves. Instead, it may become a seething, chaotic froth, a quantum foam. Picture the void of empty space not as a dark, placid sheet, but magnified by a factor of trillions upon trillions. What you would see is not emptiness, but a bubbling, effervescent turmoil. Tiny wormholes, far smaller than an atom, would constantly blink into existence, connecting two random points in spacetime for a fleeting instant before collapsing again. Spacetime itself would have a foamy, fractal structure, with every tiny bubble a potential shortcut through the cosmos. This is the Planck scale, where distances are so minuscule they have no meaning in our everyday world. Here, the concepts of before and after may lose their definition. In this frenetic foam, the very topology of the universe, its shape and connectivity, could be constantly changing. A particle might not travel a smooth path from point A to point B. It might, through quantum uncertainty, momentarily disappear into one of these microscopic wormholes and reappear elsewhere or elsewhen. This leads to a staggering possibility. If these transient wormholes connect not just different places but different times, then at the quantum level, the universe might be engaged in constant microscopic time travel. Information could be hopping backwards and forwards by unimaginably tiny intervals. It would not be a journey you could take, but a process happening everywhere all the time, beneath the notice of reality as we perceive it. The flow of time we experience, the steady tick of the clock, would then be a statistical average, an emergent property from the chaotic dance of these countless quantum connections. It would be like watching a river flow smoothly from a distance, not seeing the frantic, chaotic motion of every individual water molecule colliding and swirling. Our arrow of time, always pointing forward, might arise from the overwhelming statistical likelihood of certain quantum states, not from a fundamental law forbidding the reverse. The visual for this is both beautiful and profoundly alien. Imagine a view of empty space, but instead of black, it is a turbulent sea of iridescent blues and purples. The surface churns with ephemeral bubbles, each one a shimmering, microscopic tunnel that winks in and out of existence in a flash of silver light. Some bubbles connect to others nearby, their brief glow tracing a path. Others might flicker with a different color, a hint that their connection is not just spatial but temporal, a bridge to a moment, a Planck second in the past or future. This is the universe at its most fundamental, a dynamic, probabilistic foam where the geometry of reality is constantly being rewritten. If we could ever harness this, the implications are beyond science fiction. We would not build a time machine from gears and exotic matter. We would learn to stabilize one of these natural quantum fluctuations, to expand a microscopic wormhole into a traversable gateway, to surf the foam of creation itself. It suggests that the potential for time travel is not a rare cosmic anomaly, but buried in the fabric of every single cubic centimeter of empty space around us, waiting for a physics we have not yet mastered to reveal its secrets. Quantum foam suggests a chaotic foundation for reality, but some loops in time are terrifyingly neat and inescapable. This is the predestination paradox, a trap where every effort to escape a fate only tightens its grip, ensuring the event happens precisely as it always did. It is the universe's most perfect trap, a story that writes its own beginning with its ending. The classic example is the film The Terminator. A killer cyborg is sent from a future ruled by machines to assassinate Sarah Connor, the mother of the human resistance leader. A soldier, Kyle Reese, follows to protect her. He succeeds, but in the process, he and Sarah fall in love. Sarah becomes pregnant, and her son, John Connor, grows up to lead the war against the machines. John then sends Kyle Reese back in time to protect his mother, who is in fact his own father. The loop is sealed. Without the Terminator being sent to kill Sarah, John would never have sent Kyle back. Without Kyle being sent back, John would never have been born. The entire future war, the reason for the time travel, is created by the time travel itself. The attempt to change history is what writes it. This ignites a profound philosophical firestorm, the ancient debate between free will and determinism. If every action you take to avoid a prophesied event is actually the cause of that event, do you truly have a choice? Or are you just an actor reading lines from a script whose final page is also its first? The predestination paradox argues for a chilling kind of determinism. Your feeling of freedom, your desperate struggle, is an illusion. The timeline is a closed circle, and you are simply tracing its curve. To illustrate, let us craft a short story. A historian named Leo becomes obsessed with a minor, tragic footnote: the unsolved disappearance of a brilliant clockmaker named Elias in 1888. Using a prototype device, Leo travels back to Victorian London to warn him. He finds Elias in his workshop, surrounded by intricate gears. Leo breathlessly explains the danger that Elias will vanish on the night of the autumn equinox. Terrified, Elias decides to flee the city immediately. He packs his tools, including his unique, unfinished masterwork, a chronometer. On his way to the train station, disoriented and rushed, he takes a wrong turn into a fog-shrouded alley. There, he is struck by a runaway carriage. The driver, panicked, hides the body. The only item found at the scene is the strange, half-finished chronometer, which eventually ends up in a museum. Leo, returning to his own time, visits that same museum. In a display case, he sees the chronometer, labeled as the last known work of the missing clockmaker, Elias. Next to it is a period sketch of the alley where the body was found. In the sketch, barely visible in the shadows, is the blurred figure of a man in modern clothing, watching. It is Leo himself. His warning did not change history, it authored it. His presence in the past was not an intervention, it was a necessary component of the very event he sought to prevent. The paradox is perfect and utterly inescapable. It asks if we are authors of our destiny or merely scribes, copying a text whose first word was written by our own future hand. The predestination paradox closes a loop of inevitable fate, but another paradox threatens to burn the very concept of an event horizon to ashes. This is the black hole firewall, a modern and ferocious debate that reshapes what we think happens at the point of no return. For decades, physicists held a gentle assumption based on Einstein's equivalence principle, the idea that crossing a black hole's event horizon should be uneventful. If you were an astronaut falling into a stellar mass black hole, you would feel nothing special as you passed that invisible boundary. The true drama of stretching and crushing, spaghettification, would come later as you approached the central singularity. But in 2012, a quartet of physicists Almary, Marolf, Polchinski, and Sully published a paper that set the world of theoretical physics ablaze. Their argument, now called the AMPS paradox, suggests a horrifying alternative: to preserve the quantum information of what falls into a black hole, as required by the laws of physics, the event horizon cannot be a calm place. It must be a searing boundary, a literal wall of fire composed of unimaginably high-energy particles. An astronaut would not pass through smoothly, they would be instantly incinerated. The paradox arises from a brutal three-way clash between three cherished principles of physics. The first is the equivalence principle, which says free fall feels like floating in empty space, so the horizon should be unremarkable. The second is quantum mechanics, which says information cannot be destroyed. The third is locality, the idea that particles far apart cannot influence each other faster than light. The AMPS team showed you cannot have all three when it comes to black hole evaporation. Something has to give. Their controversial choice was to sacrifice the calm horizon. They argued that to prevent a violation of quantum information laws, the entanglement relationships between particles must break in a violent way at the horizon. This sudden, catastrophic severing of quantum links would release an enormous amount of energy, manifesting as a deadly firewall. Imagine your descent toward the black hole. The star field behind you is compressed into a brilliant, shrinking disk of light. Ahead is only darkness. You check your instruments, expecting no change as you cross the theoretical boundary. But instead, just as your sensors indicate you are passing the event horizon, your entire forward view erupts. A wall of blinding, blue-shifted radiation materializes from the void, a storm of every wavelength concentrated into a sheet of pure energy. It is not fire as we know it, but a quantum inferno, a boundary where the laws of physics themselves fracture to protect a deeper truth about information. In an instant, you and your ship are vaporized, your information scrambled and encoded onto the inferno itself long before you could ever reach the interior. This firewall presents a devastating limitation for any notion of using black holes as portals. If the AMP's argument is correct, then the event horizon is not a gateway, but a cosmic shredder of infinite temperature. The dream of plunging into a black hole to reach another universe or time dies at this first, impassable barrier. There is no graceful fall through a wormhole, no navigation of the ergosphere's currents, just immediate annihilation. The debate this sparked is one of the most heated in modern physics. Many theorists reject the firewall precisely because it violates the equivalence principle so violently. They are searching for other ways out of the paradox, suggesting that our understanding of quantum entanglement in curved spacetime is still incomplete. Perhaps the information is preserved in subtler ways, or perhaps the interior of the black hole is far more complex than we thought, avoiding the need for such a violent solution. The firewall remains a hypothesis, a terrifying possibility written in the language of quantum gravity. It serves as a stark reminder that the universe's most extreme environments may not just bend the rules, but shatter them entirely in defense of its own logical consistency. The event horizon might not be a door, but a burning curtain, and behind it, the secrets of time may be forever locked away in the ash. The firewall turns the event horizon into a cosmic executioner, but what if that protective veil were torn away entirely? A singularity stripped of its event horizon is called a naked singularity, a point of infinite density exposed to the universe for all to see. This is not a black hole, for there is no blackness, no point of no return. It is something far more bizarre and potentially dangerous, a raw wound in spacetime where the laws of physics cease to function, visible from across the cosmos. According to some solutions of general relativity, such an object could form under specific, violent conditions, perhaps from the collapse of a star with a very particular rotation or from the collision of two ultra-dense objects. Without the event horizon to cloak it, the singularity's infinite gravitational influence would reach out unimpeded, warping the fabric of reality around it in ways that are almost impossible to predict. The environment near a naked singularity would be a chaos of distorted physics. Light would follow paths so twisted that you might see multiple fractured images of the same star. Time itself would be stretched and knotted into unrecognizable shapes. Crucially, many of these theoretical models suggest that closed timelike curves would form freely in the space around the exposed singularity. It would not be a controlled gateway or an engineered machine, but a wild, natural time-warping phenomenon. A spacecraft venturing too close might find itself on a trajectory that loops back to its own past, not by design, but by the sheer, uncontrolled gravitational insanity of the object. The singularity would act less like a door and more like a storm of temporal distortion, where entering could hurl you into yesterday by accident. The visual for this is both beautiful and deeply unsettling. Against the black void of space, the naked singularity is not a dark sphere. It is a point of terrifying brilliance, a pinprick of searing white light that does not illuminate but distorts. The space around it shimmers like a heat haze, but instead of blurring, it fractures. background galaxies are smeared into luminous rings and arcs, their light bent into impossible pretzel shapes. Some light rays are captured in orbits, creating a permanent, glowing halo of trapped starlight around the singular point. The effect on time would be visible as a kind of temporal lensing. Imagine watching a probe approach this maelstrom. As it nears the chaotic zone, its signals would begin to stretch and multiply. You might receive a transmission from the probe's future before a transmission from its past, its history arriving out of sequence. The probe itself might appear to split into ghostly afterimages, each one representing a different point in its own timeline, all visible at once from a safe distance. It would be a window into the breakdown of causality itself. Yet, most physicists believe such an object cannot exist in our universe. This belief is codified in the cosmic censorship hypothesis proposed by Roger Penrose. It is a conjecture, not a proven law, but it carries immense weight. The hypothesis states that nature abhors a naked singularity. Whenever gravitational collapse threatens to produce one, the laws of physics will conspire to wrap it in an event horizon, hiding it from view and protecting the rest of the universe from its unpredictable influence. The singularity is censored, cloaked behind a one-way curtain. The reasoning is deeply rooted in the principle of predictability. In science, we rely on the idea that if you know the state of a system now, you can, in principle, calculate its state in the future. A naked singularity destroys that. Its infinite density and exposed nature mean that information could be lost into it or spewed out from it arbitrarily, making the future fundamentally unpredictable. It would be a source of true randomness, not quantum probability, but classical chaos that could rewrite physics on a whim. The universe, according to this hypothesis, values order and predictability enough to forbid such monsters. They are locked away in the vaults of black holes where their infinite weirdness is contained. So the search for naked singularities becomes a test of nature's own rules. If we ever found one, it would overturn our understanding of gravity and causality. It would mean the cosmos allows for visible time machines and regions of lawless physics. Until then, they remain theoretical ghosts, the ultimate forbidden objects, suggesting that some doors are kept locked not by chance, but because the universe itself is guarding the keys. The cosmic censorship hypothesis locks away the most lawless singularities, but even the cleanest theoretical time machine faces a universal shortage of fuel. At the heart of wormholes, warp drives, and other engineered shortcuts lies a single, staggering requirement: exotic matter. This is not merely rare or powerful material, it is a substance that defies the fundamental behavior of everything we know. Normal matter, from stars to stardust, possesses positive energy density. Its gravity attracts curving spacetime inward like a weight on a trampoline. Exotic matter would need negative energy density, producing a kind of anti-gravity that pushes spacetime outward, propping open the throat of a wormhole against its own fierce urge to collapse. Imagine trying to hold open a spring-loaded trapdoor with infinite pressure slamming it shut. Your hands are normal matter, futile against the force. Exotic matter would be like a magical rod that, when placed in the doorframe, actively pushes the door open, creating a stable passage. The diagrams are starkly contrasting. One shows a normal star, its mass creating a deep, funnel-shaped depression in the grid of spacetime. The other shows a theoretical lump of exotic matter as a glowing, purple sphere, not creating a depression but a hill, a bump that pushes the spacetime grid upward around it. To create a traversable wormhole, you would need to line its narrow throat with this hill-making material, forcing the tunnel to remain open against the crushing weight of the universe's geometry. So where could such a bizarre substance possibly come from? Our only hint lies in the ghostly realm of quantum mechanics. Even in a perfect vacuum, utterly empty space is not truly empty. It seethes with virtual particles, pairs of particles and antiparticles that flicker into existence using borrowed energy. only to annihilate each other and vanish an instant later. This quantum froth has a tangible effect known as the Casimir effect. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, something remarkable happens. The plates are so close that only certain wavelengths of virtual particles can pop into existence between them. Outside the plates, all wavelengths are possible. This creates a subtle pressure difference, and the plates are pushed together by the force of the virtual particles outside. Crucially, the energy density between the plates is lower than the energy density of the pure vacuum outside. In a very specific technical sense, this region between the plates exhibits negative energy density. It is a microscopic hint that the universe does permit such things, but on a scale almost too small to comprehend. The amount of negative energy in a Casimir setup is infinitesimal. To stabilize a wormhole large enough for a proton to pass through, you would need a negative energy equivalent to the mass of Jupiter concentrated in that tiny space. For a human-scale tunnel, the required exotic matter would outweigh the entire visible universe. The engineering challenge is beyond colossal. It is laughable with our current understanding. We are looking at the faintest whisper of a phenomenon and trying to imagine it as a cosmic shout. This exotic matter problem is the ultimate showstopper for many elegant time travel blueprints. It transforms a theoretical possibility into a practical impossibility, a door with a lock for which we cannot even conceive of a key. It suggests that the universe may allow time travel in its mathematical heart, but surrounds that permission with a moat of impossible physics, a barrier not of fire or censorship, but of sheer, unimaginable scarcity. Exotic matter may be the universe's rarest fuel, but nature has already crafted structures that dance to the beat of time itself. In laboratories around the world, scientists have created something that sounds like pure science fiction: time crystals. Unlike any other form of matter, a time crystal does not settle into a stable, lowest energy state. Instead, it oscillates, it ticks in a perpetual, repeating pattern without any energy input. It is a clock built into the very fabric of a quantum system. The secret lies in a concept called symmetry breaking. Most physical systems obey time translation symmetry, meaning their properties look the same whether you observe them now or 5 minutes from now. A time crystal shatters this symmetry. Its components, like a ring of ions or a lattice of spins, are arranged in a pattern that repeats not just in space but in time. They flip from one configuration to another and back again with a rigid, predictable period forever. It is as if you had a diamond that, instead of just sitting still, constantly rotated its facets in a perfect, endless cycle, powered by nothing but the strange rules of the quantum world. The visuals for this are mesmerizing. Picture a ring of glowing points like pearls on a necklace. They are not static. In a steady rhythm, each pearl pulses, its color shifting from blue to gold and back again, but the pattern around the ring is always offset. The blues and golds chase each other in a never-ending cycle, a luminous carousel that turns without any engine. Diagrams show this as a spiral through space-time, a helix where one full turn represents a complete cycle in time, proving the structure's order exists across the fourth dimension. So what could this possibly have to do with time travel? The connection is speculative but profound. Time crystals demonstrate that temporal order can be a tangible, engineered property of a system. They are a proof of concept that we can create matter with a built-in rhythm that resists the universal drift toward equilibrium. Some theorists wonder if, by scaling up this principle or coupling time crystals with other extreme physics, we might learn to imprint more complex temporal structures onto space-time. Could a network of time crystals be used to stabilize a region of distorted time, like the chaotic quantum foam? Might they act as a resonator, amplifying or dampening specific temporal frequencies around a potential wormhole? The field is in its infancy, a first trembling step into the active manipulation of time as a material property. We are not building portals yet, we are learning to make the fabric of reality hum a specific tune. This changes the question from one of colossal engineering to one of exquisite control. It suggests that mastering time may not require moving mountains, but learning to conduct the silent, perpetual symphony already playing within the atoms all around us. Time crystals show us matter that dances to a silent, eternal rhythm, but a simple question has haunted physicists for decades. If time travel is even remotely possible, where is everybody? This is the anthropic argument, a philosophical puzzle that uses our own existence as evidence. The universe is ancient, over 13 billion years old. Intelligent life, at least here on Earth, arose relatively recently. If time travel technology is possible to develop, then logically, someone, somewhere in the vast expanse of the future would have invented it. And once invented, the entire past becomes a tourist destination. We should see visitors from the future everywhere in our history, at every major event, subtly or overtly changing the course of human affairs. Yet our historical record shows no conclusive proof. There are no anachronistic artifacts, no clear messages etched in stone, no photographs of futuristic observers at the Battle of Waterloo. The silence of history is deafening, so why the empty streets of time? Several compelling answers have been proposed, each a theory in its own right. The first is the simplest: time travel to the past is fundamentally impossible. Perhaps Hawking's chronology protection conjecture is a law of nature, and the universe erects a firewall of quantum fury to stop any paradox before it begins. Our equations might hint at tunnels and loops, but reality fills them with infinite energy or instability. We are alone in history because the past is a castle with drawbridges permanently raised, its walls guarded by the laws of physics themselves. The second answer is practical. Time travel might be possible, but it is prohibitively expensive or difficult. Building a wormhole could require the energy output of a galaxy. Stabilizing it might need exotic matter that is virtually unobtainable. Or perhaps the technology is so delicate that only microscopic probes could be sent back, undetectable to our primitive senses. The tourists are not here because the ticket price is the mass of a star, and the journey is a 1 in a billion gamble. The third answer is sociological. The tourists are here, but they are hiding. A future society with the power to visit the past would likely have strict ethical protocols or non-interference directives, like a cosmic version of a wildlife preserve. They would observe from cloaked ships or microscopic drones, careful to leave no trace. Every unexplained historical mystery, every strange light in the sky, every odd character who seemed to know too much could be a potential sign of their discreet presence. We are not alone, we are simply being studied by experts who know how to remain unseen. The fourth answer comes directly from the many worlds interpretation. Time travel is possible, but it always creates a new branch of reality. In this view, tourists from the future do arrive all the time, but the moment they step into our past, they split off a new parallel universe. Our timeline, the one we are living in and recording in our history books, is a branch where no time travelers ever arrived. We are the universe that got left behind, the quiet, unvisited version of history. It is a strangely lonely thought. We are not the main attraction. We are the deserted street no one chose to walk down. So which explanation feels most true to you? Does the universe forbid it outright? Is the technology forever out of reach? Are we being watched by invisible guests? Or do we inhabit a timeline that simply never received a postcard from tomorrow? Cast your vote in the comments below, and let's see which theory resonates most with this curious community of cosmic wanderers. Silence from future tourists might not mean time travel is impossible, only that we are looking in the wrong place. What if the past is not a physical destination but a saved file? This leads us to a theory that reframes everything, the simulation hypothesis and its radical implications for time. The idea is simple yet staggering. Our entire universe, with its galaxies, black holes, and conscious beings, might not be the base layer of reality. It could be an artificial construct, a simulation running on a computer of unimaginable power in a higher dimensional reality. Think of a hyper-advanced video game so perfectly rendered that its inhabitants believe their world is real. In such a simulation, every law of physics is just a line of code. Gravity, the speed of light, even the flow of time are programmed parameters. And just as you can rewind a movie or load an old save file in a game, the operators of our simulation could, in principle, rewind the universe. Time travel, in this view, would not involve bending space-time with exotic matter. It would be an administrative function. An operator could simply roll back the cosmic clock to a previous state or copy a segment of the code and run it again with different variables. The past is not gone, it is stored data waiting to be accessed. This idea finds a vivid parallel in the film The Matrix. Recall the scene where Neo first visits the construct, the blank white loading program. Morpheus explains that they can load any training simulation they need, from basic combat to a crowded city street. They are not traveling to a physical location in the past, they are calling up a fully realized historical environment from the system's memory. In a similar way, if our reality is simulated, a journey to the 1800s would not require a wormhole to Victorian London. It would require accessing the saved instance of the universe from that date and rendering it for the traveler, or perhaps inserting the traveler's consciousness into an avatar within that saved world. This also provides a framework for understanding bizarre, seemingly paranormal events that resemble time slips or glitches. A person who briefly sees a scene from another era or an object that appears out of its time might not be experiencing a fracture in space-time but a temporary bug in the simulation. A memory leak, a corrupted asset loading from the wrong temporal file, or a debugging tool left visible by a careless operator. These anomalies would be the equivalent of seeing a character from one game world suddenly appear in another, a clear sign of the underlying code. The visual for this theory is a blend of the cosmic and the digital. We see the familiar spiral of a galaxy, but then the camera pulls back to reveal it is a glowing, intricate network of luminous data streams, a neural network of light on a cosmic scale. A segment of the network representing a century of Earth's history pulses. An operator's command, represented by a beam of pure information, touches that segment and it blossoms open, replaying its events in fast reverse like a rewinding film. Within that replay, a single point of light, a simulated consciousness, is lifted out and placed back into the stream at an earlier point. It is not a physical journey but a data transfer. This perspective dissolves many of the thorniest paradoxes. The grandfather paradox is just a logical inconsistency in a narrative, something a simulator could easily debug or run in a sandboxed environment to observe the outcome. The Novikov principle might simply be a rule enforced by the simulation's core programming to maintain narrative consistency and conserve processing power. Even the eerie silence of time tourists makes a new kind of sense. If we are in a simulation, then the operators likely have strict protocols against revealing themselves to avoid crashing the simulation or provoking an existential crisis in its inhabitants. Their visits would be utterly undetectable, happening in a debug mode invisible to us. The simulation hypothesis transforms time from a fundamental river into a controllable variable, and time travel from a cosmic engineering challenge into a question of user permissions. It asks us whether the mysteries of black holes and quantum foam are features of reality, or just especially elegant lines of code in a program we are only beginning to suspect exists. Consciousness might be the only time machine we will ever truly possess. While physics charts the geometry of space-time, our own minds already bend time in subtle, mysterious ways. Precognition, the fleeting sense of knowing something before it happens, and déjà vu, that eerie conviction you have lived this exact moment before, are common human experiences that science struggles to explain. They feel like glitches in the matrix of linear time, brief moments where the orderly sequence of past, present, and future seems to blur. Some speculative theories propose that these are not mere neurological misfires, but faint whispers of a deeper truth, that consciousness is not a product of the brain, but a fundamental aspect of the universe like gravity or electromagnetism. In this view, the mind is not locked inside the skull, ticking along with the body's clock. It is a non-local phenomenon, existing in a realm where time is not a river, but an ocean. You are not floating downstream, you are the ocean itself, aware of all its currents and depths at once. The brain, then, is not the generator of consciousness, but a receiver, a biological instrument tuning into a signal that transcends space and time. It filters the vastness into the narrow, manageable stream we experience as the present moment. But sometimes the filter slips. In moments of deep meditation, intense crisis, or even in dreams, the receiver might pick up a fragment of information from a wavelength outside the standard broadcast, a faint signal from a future possibility or a past resonance. This connects to the controversial idea of the quantum mind. Some theorists suggest that microtubules, tiny structures within our brain cells, might harness quantum processes like superposition and entanglement. If our cognition has a quantum component, then perhaps it participates in the same non-local, timeless network that links entangled particles. Your conscious observation of the world might not just be a passive recording, but an active participant in weaving the tapestry of time, with your attention pulling certain threads of possibility into reality from a cloud of potential futures. The imagery for this is surreal and dreamlike. Picture a person standing in a vast, dark space. Instead of a timeline stretching before them, they are at the center of a shimmering, four-dimensional web of light. Each glowing strand represents a possible event, a memory, a future choice. The web pulses and shifts with their focus. When they think of a past regret, a cluster of strands behind them brightens. When they feel anxiety about tomorrow, a different cluster ahead flickers into view. They are not moving through the web, they are the point from which the entire structure radiates. In a moment of precognition, a single strand far out in the future network pulses brilliantly, sending a shockwave of light back along its length to the center, manifesting as a gut feeling or a vivid dream. Déjà vu is represented by a strand from the past that, for an instant, perfectly overlaps with a strand in the present, creating a double exposure of experience. This perspective turns time travel from an external engineering problem into an internal exploration. The journey to yesterday or tomorrow would not require a ship, but a profound alteration of consciousness, a deliberate retuning of the receiver to a different frequency of the timeless ocean. Mystics and shamans have sought this for millennia through ritual and trance, attempting to step outside of time's flow. While this sits far outside mainstream science, it challenges a fundamental assumption that time is purely a physical dimension. What if it is also a dimension of mind? What if every black hole's twisted space-time and every wormhole's impossible tunnel has a counterpart in the labyrinth of a consciousness unshackled from its biological clock? The greatest journey through time might not begin with a launch into space, but with a descent into the depths of our own awareness. Our minds may wander through time's labyrinth, but physics demands a single, unbreakable map. For a century, the universe has been telling two different stories. One story, written by Einstein, describes the grand cosmic stage, where gravity is the curvature of space-time by mass and energy. It is a story of planets, stars, and black holes, a tale of smooth, geometric beauty. The other story, written by Bauer, Heisenberg, and others, describes the frantic, probabilistic actors on that stage. It is a story of particles that are also waves, of spooky entanglement, of a world built on chance and uncertainty. These two stories are both magnificently successful, yet they speak different languages and contradict each other at the extremes. Where they clash most violently is at the singularity of a black hole and in the first moments of the Big Bang, precisely the realms where our questions about time's true nature become most urgent. The dream, the final great theory, is to weave these two narratives into one. This is the quest for a theory of everything, a single framework that explains all forces and all particles under one set of principles. Such a theory would not just complete physics, it would hand us the ultimate owner's manual for reality. It would tell us once and for all if the loops and tunnels we have explored are real possibilities or beautiful mirages in the math. It would define the limits of the possible. Currently, the leading candidate for this unification is string theory. Its premise is elegant yet profoundly strange. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. Each distinct vibration pattern corresponds to a different particle, an electron, a quark, a photon. In this view, gravity, carried by the hypothetical graviton, is just another note in the string symphony. The theory requires extra dimensions beyond the three of space and one of time we experience, dimensions curled up so small we never notice them. The implications for time travel within string theory are tantalizing and complex. The extra dimensions could provide new pathways, new geometries for closed timelike curves to form. Some solutions in string theory suggest stable wormholes might be possible without the need for impossible exotic matter, perhaps by using the properties of these hidden dimensions to stabilize the tunnel. The theory also provides a concrete, if highly abstract, picture of what happens at a singularity, potentially resolving the paradoxes of infinite density and offering a quantum description of a black hole's interior. Another promising path is loop quantum gravity, which imagines spacetime itself is not smooth, but woven from a network of discrete, finite loops. In this view, there is no such thing as a true singularity, a point of infinite density. Instead, gravity becomes so strong that it causes a quantum bounce, potentially turning a black hole into a gateway to another region of spacetime. This could naturally lead to wormhole structures within the fabric of this quantum weave. But a theory of everything would do more than just validate or invalidate blueprints. It would reveal the fundamental architecture of time. Is time a fundamental ingredient or an emergent property that arises from the quantum connections between events, like temperature emerging from the motion of molecules? The answer dictates everything. If time is emergent, then traveling backward might be as nonsensical as trying to unfry an egg, a statistical impossibility rather than a geometric one. The ultimate visual for this final theory is one of breathtaking simplicity emerging from incredible complexity. Picture the cosmos in all its splendor, galaxies swirling, black holes lurking, quantum particles flickering. Then the camera pulls back, and all of this, every force, every particle, every moment of history, is seen to flow from a single, luminous equation hovering in the void. Its symbols are not just numbers and letters, but shimmering strands that twist into the shapes of strings and loops, of curved spacetime and probability clouds, all harmonizing into one coherent, elegant expression. It is the universe's signature. Finding this equation is the great unfinished work of science. It is the key that could lock the door to time travel forever, or finally, after 30 journeys through possibility, hand us the key to open it. From cosmic strings to quantum foam, from the silent library of the holographic universe to the fiery veto of the chronology protection conjecture, we have charted 30 extraordinary paths through the landscape of possibility. Each theory, whether a ghost in the mathematics or a storm at the edge of a black hole, represents a profound attempt to answer one of humanity's oldest and most compelling questions. Can we touch yesterday or visit tomorrow? The journey reveals a stunning truth: our universe, in its deepest laws, does not slam the door on time travel. It leaves it tantalizingly ajar, guarded by paradoxes and propped open by exotic matter we cannot find. While no one has yet built a time machine or received a postcard from the future, the very act of exploring these ideas is a form of time travel in itself. We use the equations of general relativity to peer into the hearts of collapsing stars from billions of years ago. We employ quantum mechanics to listen to the faint whispers of the universe's first moments. We are travelers using the mind as our vessel and curiosity as our fuel. The greatest discovery from this journey may not be a blueprint for a machine, but a deeper reverence for the fragile, consistent flow of time that makes our story possible. It is the canvas upon which all life, love, and discovery are painted. So now the question turns to you. Which of these 30 theories captured your imagination most completely? Was it the elegant trap of the predestination paradox, the cosmic escape hatch of the white hole, or the silent observation of a universe that might be a simulation? Cast your vote in the comments below and let's continue the conversation. Speculate, which of these mind-bending ideas do you think will be the first to find a hint of evidence, a shadow in our data, or a glitch in reality's matrix? The adventure does not end here. If you crave more journeys to the edge of understanding, more deep dives into the cosmos's greatest secrets, make sure to subscribe. Together, we will keep exploring the magnificent and mysterious universe we call home.